Welcome to the last part of Lecture 3. Here we're going to talk about something called LeChatelier's principle. So what is LeChatelier's principle? Well, one, it applies to reactions that are at equilibrium and then get disturbed out of equilibrium in some manner. And so LeChatelier's principle provides a nice rule to determine which way a reaction will go in order to restore equilibrium after some disturbance is applied. The one thing to remember about the equilibrium point of a reaction is it is essentially the lowest energy point for that reaction, and so that's where reactions try to get to. They always try to reach that point of equilibrium, and if you throw something out of equilibrium, it's going to try to re-reach in equilibrium. Some of the different things that we can do to a reaction at equilibrium in order to disturb that equilibrium is to change the concentration of one of the reactants or the products, either by adding or removing. If we have a gas phase reaction, we can change the pressure or change the volume. Or one of the last things we can do is to change the temperature. Any of these things can throw a reaction out of equilibrium, create that disturbance, and what LeChatelier's principle provides to us is how is that reaction going to respond. So if we look at LeChatelier's principle just kind of as a definition, it says if an external stress is applied to a system at equilibrium, the system will adjust to partially offset the stress and restore equilibrium. The two words very important in there, partially offset. When you disturb a reaction at equilibrium and you do something to it, either adding or removing a reactant or product or change temperature, that reaction has been disturbed more or less permanently. Not to that point, but you have to get back to a point of equilibrium, but it will not be exactly the same as it was before the disturbance was applied. So let's look at concentration change. Let's look at this reaction here at equilibrium. So we have a complex ion, iron thiocyanate, FeSCN2+. It's in equilibrium with its two components, iron 3+, which is yellow, thiocyanate ion, which is colorless, and then you have the iron thiocyanate complex, which is very deep red. We do have an equilibrium constant expression there, so we have our products, iron 3+ times the thiocyanate ion concentrations over concentration of the complex. Now, if we were to add sodium thiocyanate, so sodium thiocyanate is a salt. Because it's a sodium salt, it's fully soluble in water and it will dissociate in water into sodium ions, which we don't really care about, but it does produce thiocyanate ions. Now, what we see if we add some thiocyanate, even though thiocyanate itself is colorless, the solution turned more red. Well, why is that? Well, one of the things we did was to increase the thiocyanate ion, so that disturbed the equilibrium. Remember, the reaction was at equilibrium. I had the exact amounts of FeSCN2+, Fe3+, and SCN- to be at equilibrium. And then I threw it out of equilibrium by adding something that's part of the equilibrium constant expression. So my concentration of iron thiocyanate went up. Okay, so now it's too high. What does that do to the equilibrium constant? Well, if my SCN concentration is too high, it means that my numerator is too high, and that means that my Q value would be bigger than my K value. So we know that Q in this case would be bigger than K. And if Q is bigger than K, what we learned is that that reaction needs to shift back towards the reactant side in order to restore equilibrium. Okay, so when it shifts to the left to restore equilibrium, what it does is it creates more of the iron thiocyanate ion, which has that deep red color, and as a result, we get a deeper red color in that solution. Pressure and volume changes can be a little bit tricky. They only apply if you have gases present in your reaction. If Everything that you have is in a condensed phase, and when we say condensed phase, we mean like a liquid or a solid. They are not affected at all by pressure and volume changes. Only gases there. So liquids and solids don't compress. So as a result, the number of moles, which is how much material is there, you certainly can't change that by changing pressure and volume. But volume doesn't change because you can't really change the volume of water just by pushing on it. And so that number of moles per volume remains the same. As a result, the concentration stays the same, and you're not throwing anything out of equilibrium. Gases, however, do compress, and as you compress a gas, its concentration will go up, or you can expand a gas and then its concentration would go down. If you're changing the concentrations of one thing or another, then you're going to throw it out of equilibrium. So the concentration will change most for the species with the largest stoichiometric values, and that's a little confusing. But if you, when you change the pressure on a gas phase reaction where everything's a gas, you're changing the pressure for everything. You can't just change the pressure for one thing. Anything that's a gas will change. But the concentration is going to change most for the species that has the largest stoichiometric value in the balanced reaction. So that means that if you increase the pressure by lowering the volume will drive the concentration up. It will make a greater effect on something with a larger set of coefficients. So you need to look at the sum of coefficients in the reactants, sum of coefficients in the products, and do some comparison there. So as we mentioned, when we increase the pressure, the reaction will shift to, if we want to summarize that previous slide, when the pressure is increased, the reaction will shift to the side with the fewer numbers of moles of gas and vice versa. Another way to think about this is if you increase the pressure, the system says, whoa, that's a lot of pressure. How can I reduce that pressure? Well, if you have fewer moles of gas, you're going to have less pressure, so it's going to shift to the side that has fewer numbers of moles because that will decrease the pressure and help decrease the effect of the added pressure. So for example, on this side, we have 2 PBS solid plus 3 O2 gas goes to 2 PBO solid plus 2 SO2 gas. Now, if I were to increase the pressure, so that's the P there, not the P in the chemical formula, it's just pressure. If I increase the pressure, notice that I've got 2 moles of gas in the reactant and 2 moles of gas, 2 moles of gas in the product and 3 moles of gas in the reactant there. So if I increase the pressure, the reaction says, I just got a lot of pressure increase. How can I decrease some of that change? How can I remove some of that change? Well, it wants to shift to the side that has fewer numbers of moles of gas. So if I increase the pressure, it's going to shift to the right because that will take you to 2SO2. You'll have fewer moles of gas if you make more product, and that will lower the pressure inside the vessel. Okay, what happens if volume is increased? Well, if I were to increase the volume, that essentially lowers the pressure. So if I lower the pressure, the system says, oh, I'm losing pressure. How can I create more pressure? Well, you can create more pressure by shifting to the side that has more moles of gas. And so if I increase the volume or lower the pressure, the reaction will shift over towards the side with more moles of gas, and that would be towards the left or towards the reactants. And there's another example there that you can look at. So what about temperature changes? Now, when we change concentrations or change pressure or volume, we change the position of equilibrium, but we haven't changed the constant. So when those types of changes throw a reaction out of equilibrium, the equilibrium that it settles back at will still have the exact same equilibrium constant value when it reaches equilibrium. However, if I change the temperature, generally I'm going to change the value of K, the equilibrium constant. So you may say, well, if you change the equilibrium constant, how do we know which way it's going to shift to get back to a brand new equilibrium constant? Well, it turns out we can still do it by looking at the enthalpy of the reaction or the heat of the reaction, because temperature involves heat. So if a reaction is endothermic, in other words, heat needs to be added to the reaction, then we treat heat as a reactant. So if it's endothermic, we treat heat as a reactant. We know a reaction is endothermic if it has a delta H that is positive. And if a reaction is exothermic, then we are going to treat heat as a product. Exothermic means heat is coming out. It would be something that's hot, so it's producing heat. That's one way to think about it. So we're going to treat heat as a product. And one way to recognize an exothermic reaction is that your delta H is going to be negative. Okay, so increasing temperature is like adding heat. Decreasing temperature is like removing heat. So by making heat a reactant or a product, then increasing or decreasing temperature is like adding or removing heat. Then we can treat it really easily with LeChatelier's principle. So let's look at this reaction here. So we've got N2O4 goes to 2NO2. It has a delta H of plus 55.3. So we see that positive delta H there. That means that the reaction is endothermic. That means that I want to write plus heat on the reactant side. So now I have heat on the reactant side because it's endothermic. So this kind of helps me out. So what happens when I increase the temperature? Okay, well, if I increase the temperature, let's see, we'll just write an increase in T. Okay, if I increase the temperature, that's like adding a reactant. Okay, and if I add a reactant, the reaction says, oh, I've got too much reactant now. I need to shift towards the product side. And by shifting towards the product side, I'm going to make more NO2, which is going to turn it brown. And we see over here in our little diagram here, these are sealed tubes of NO2. So it's in equilibrium with N2O4. And we've got room temperature here. We've got one in ice on the left, and we've got one in hot water on the right. Notice in the hot water, we have a much browner mixture because that reaction has shifted more towards the products and created more NO2. If I cool things down, if I remove heat, so I lower the temperature, that's like removing a reactant. And so the reaction says, oh, I had something removed, I want to replace it. So if I remove heat, it wants to replace the heat. How does it replace the heat? It shifts that reaction in the reverse direction. And so that removes the brown, it moves it more towards a colorless gas, N2O4, and the reaction, or the equilibrium mixture becomes less dark. This is actually what happens in a lot of cities that have a heavy amount of pollution due to vehicle traffic. NO2 and N2O4 are primary exhaust components, and so air in those big cities where, like Los Angeles, where things get kind of bottled in, their air pollution is really bad in the summer where you get that brown cloud hanging over the city. That's due to more NO2 during those hot days. During the winter months, it's not as bad because you have N2O4. And one of the big issues with NO2, more NO2 being present in the air, it becomes something that you breathe in. When it reacts with water, it forms nitric acid. And if you can imagine breathing in some NO2 and it interacts with the moisture in your nose or throat or lung tissues, getting a little bit of nitric acid right there, right on that soft tissue, yeah, it's not so nice. Chatelier's principle works also even when the equilibrium constant changes. It tells us which way things are going to shift. Now, one last thing that we need to talk about as far as equilibrium, because this is something that can affect the position of equilibrium, but not the equilibrium constant, is the addition of catalysts. So catalysts are substances that are added to a reaction in order to increase the reaction rate. They have some very special characteristics. One of the main characteristics is that they are not consumed during the reaction. In other words, all the catalysts that you put into a reaction, you're going to get back out. Now, they are used during a reaction, but they get regenerated by the reaction. And that's nice because a lot of times your catalysts, your physical catalysts, are very expensive metals like platinum or palladium, things like that. And so those are expensive metals, but what you put into a reaction, you can recover most of it and reuse it again and again. Now, how do catalysts work? Well, what they do is they change the mechanism of a reaction. So we talked about reaction mechanisms earlier in the lecture in an earlier installment there, and we saw that we have certain activation energies for all of our different reactions, and that's because you had an activated complex at that transition state that was high energy. Well, if you can add something different to that reaction that changes the energy of that activated complex to something that's lower, and now you have a lower activation energy, well, we learned that that will create more molecules or allow more molecules to get up and over that activation energy barrier, and that will increase the number of products that you get. So two things with the catalyst: they are not consumed during the reaction. They do not change the equilibrium constant, so they do not change whether you have, where your equilibrium lies. What they do change is the speed of the reaction. So they don't change what products you get, they just change how fast you get it. So it affects both the forward and reverse reactions because it lowers the activation energy for the reaction in both directions. That's why it has no effect on equilibrium, but it does get you to that equilibrium point quite a bit faster. Okay, that was the last part of lecture 3. We had some complex material in there, so if anything during any of those little parts of the lecture confuse you, as always, please make sure you contact me.